Did you know that in microgravity, you can better study the boiling process? Boiling is a very common process in our everyday life. In a wider view, boiling is encountered in many engineering fields, such as environmental applications and industrial chemical processes. What is more, understanding the dynamics of boiling is essential to improve energy production and conversion in power plants, and to design future space applications like cryogenic fuel storage and propulsion. There is consequently a great diversity of situations in which boiling occurs and must be well understood. Here on Earth, its properties and effects are too fast to be accurately observed and measured. But experiments conducted in low-gravity environments, like on the International Space Station, allow us to observe phenomena like phase transition and the onset of bubbles much more clearly.
We investigate these boiling processes in space mainly for two reasons. First of all, because today's design methods are based on empirical knowledge and not really reliable when choosing, for example, new fluids or sophisticated microstructured wall geometries. Doing experiments in zero-gravity environment has the big advantage that the boiling process takes place in slow motion. That means we can investigate more details with higher resolution than on Earth. Second, modern space technology makes use of more and more electronic devices that have to be cooled very efficiently. Flow boiling is an excellent process to do so. In a team of European scientists, we tested many different components and preliminary setups in our labs on ground, as well as in many parabolic flights. This has led to the final experimental setup of Ruby. Ruby is an experiment to study the basic heat and mass transport phenomena in pool boiling and flow boiling systems.
In terrestrial application, boiling is a very efficient means of heat transfer, and efficient boiling relies on vapor removal away from the surface, which is driven by gravity. In microgravity, of course, this doesn't occur, so bubbles are not removed from the surface. Therefore, in Pisa University, we are investigating an innovative way to replace buoyancy with electric force in order to have vapor removal also in microgravity. Previous experiments we made in parabolic flight, drop towers and sounding rocket demonstrated that the electric force may replace buoyancy, removing bubbles away from the surface, and furthermore it destabilizes the interfaces. That is, it's more difficult that a stable layer of vapor is created over the surface, and this stable layer of vapor, of course, is insulating the surface, degrading heat transfer. Furthermore, electric force may give also an alternative mean to separate phases in microgravity, and this may bring applications also in, for instance, in biological systems like bioreactors or analytical tools like mass spectrometries.
So one of the major thermal problems with satellites and space platform is to removing the heat from the devices in order to ensure suitable environmental and working conditions. Since heat transfer capability associated with phase change is typically large, this solution could lead to a decrease of size and weight of the thermal systems. But flow boiling is a very complex phenomenon which implies heat and mass transfer and also flow hydrodynamics and interfacial phenomena. Furthermore, gravity affects the fluid dynamics and may lead to unpredictable performance of thermal management system. And as you can see on the video with a comparison with microgravity and normal gravity experiments, you can see difference in the bubble size, and it will lead to a significantly decrease of the heat transfer in microgravity conditions.
So why we are here on zero-G aircraft? Because we are testing our cooling system that uses evaporation and condensation, two very, very high efficient heat transfer mechanism. Our system has been developed to cool down power electronics, in particular CPU of computers or power electronics that we can find in electric cars like inverter and batteries, for example. Gravity acceleration, in particular inertial forces, affect heat transfer coefficient of two-phase cooling system. So with this kind of test, we can make experiments of our system in this particular aircraft to test the future cooling system for electric cars and for avionics and space applications.
Performing tests in microgravity conditions is necessary in order to better understand the boiling process. Such studies may lead to the increased energy efficiency of several applications here on Earth, from power plants to thermal management systems used in electric vehicles, laptops, and smartphones, to name a few examples. Do take advantage of the opportunities and capabilities that are available for your research and development to further grow and extend your achievements. Do take the next step, the step to space. We already did.